Hello students, we are going to be learning about differential equations and slope fields. So we're actually going to skip ahead for now to section 8.3 in our spiral. Before we get started, let's just talk about what is a differential equation. So we know the word differentiate means to take the derivative. So differential equations are just equations that involve a derivative. In this lesson, in these lessons pertaining to 8.3, we're going to address three big objectives. So the first thing after this first video that I want you to understand is that we want to answer the question, what is a differential equation and what does it mean to solve one? The second thing that we're going to understand together is what is a slope field. And lastly, we are going to, in this class, learn to solve a very specific type of differential equation. And just be advised, and maybe you know this already, there are entire classes in college, we even offer one at Eagle Crest, that are just dedicated to solving differential equations. So we are only going to kind of brush against the surface of what it means to solve differential equations. So if we get started on page 114 in our spiral, there's a couple of examples in the text of differential equations. So if we look at this first one together, y double prime minus 3y prime plus y equals 0. Well, we know it's an equation because it has an equal sign. It's a differential equation because it involves derivatives, y prime and the second derivative of y. And lastly, we could specifically call this a second order differential equation because y double prime is a second order derivative. The one that's beneath that, dy dx equals 2x minus y, that's just an example of a first order differential equation because dy dx is the same as saying y prime, it's just different notation. All right, so before we try this first example, if we just recall like algebraically what it means to solve any equation, and if we look at a really easy one out to the side, going out to no man's land, let's say 3x plus 6 equals 12. We'll make it really easy. So if we were in Algebra 1 and I asked you to solve this equation, certainly you would, invert the order of operations. We would subtract 6 from both sides to get that 3x must equal 6. We would divide both sides by 3, therefore x must be equal to 2. And then we could say that x equals 2 is the solution to the equation 3x plus 6 equals 12. And it's the only solution since that was a linear equation. So if I think what does it mean that x equals 2 is the solution? Well, I could substitute 2 for x in my original equation and write 3 times 2 plus 6 equals 12. And then following the order of operations, I would get that 6 plus 6 equals 12. Therefore, 12 equals 12. So the solution to this linear equation is the number 2, that when substituted for x, makes the original equation true. We'll get into this a little bit later, but we'll find that there are multiple solutions for differential equations. So let's look at this first example. We are given that y equals e to the power of 3t. We're told that that is a solution to the differential equation y double prime minus 2y prime equals 3y. And something that I don't think I stressed above a moment ago, so let me just go back to that real fast, is that when we talk about a solution, when we solve a differential equation, we're actually going to get a function. So it's not just going to be a number, rather we're going to solve for a function. So in this example, this function that we're given, this exponential function, is a solution to the differential equation that we're working with. So when we're asked to show it, when we're asked to show that that's true, well, we know it's true from that language, we just have to do the work to prove that. So if we look at the equation that we're working with, we already know what y is, but we need the first and second order derivatives of y with respect to x. So let's find those real fast. So y prime, I'm just going to use the chain rule here. So e to the junk times the derivative of the junk, and that is 3e to the 3t. And then for my second derivative, I can just take the derivative of that. So still just the chain rule. So 3e to the 3t times the derivative of the junk, which is 3. So we get 9e to the 3t. All right, so to show that y equals e to the 3t is a solution to this differential equation, we can now plug each of those components into that differential equation and just do some math. So as we substitute those in, for y double prime, the second derivative, I'm going to substitute 9e to the 3t, and then minus 2 times the first derivative, so minus 2 times 3e to the 3t, and that equals 3 times y. And going back to what we were given for y, we said y is equal to e to the 3t. All right, so if we just follow the order of operations here, I know that I can multiply 2 by 3 over here. So let's see, we get 9e to the 3t minus 6e to the 3t, and that equals 3e to the 3t. Now, just to take this all the way home to show that these are equal, we could then just combine our like terms on the left. I can see that I could really just subtract those coefficients. So 9 minus 6 is 3. So we're left with 3e to the 3t equals 3e to the 3t. So we have shown that the function y equals 3t is a solution, not necessarily the only solution, to the differential equation y double prime minus 2y prime equals 3y. So lastly, if you were wondering, like, where do differential equations exist in the real world, for example, there are a lot of applications of differential equations. Oftentimes in the real world, we will have a rate. So it will be like we will have a known rate that we're working with. And when you're working with rates, you are working with equations that involve derivatives, rates of change. So I jotted down a couple of examples for you. So in medicine, for instance, we often use differential equations to understand the spread of disease. In engineering, to describe the movement of electricity. In physics, to model wave motion. In economics, to find optimum investment strategies, for example. And in chemistry, modeling chemical reactions. So this is certainly math that's going to be applied in many diverse areas of study.